Okay, so this is my first application of Faraday's law. And my first example, the way that I'm going to change the flux is by changing the magnetic field itself with time. So let me explain my situation. The source of my magnetic field is going to be a solenoid, a very long or infinite solenoid. It's going to have a radius, outer radius A, which is 2 meters, which I can label here. And you'll see shortly why I'm choosing to label that with an A. It's because I've got the letter R, both lower and uppercase, reserved for other things. So I just needed some other variable. And what I'm going to have is that this current is going to change with time such as to cause a magnetic field rate of change inside there, which is 5 teslas per second. And I'm going to say it's increasing. So the current here, I can wrap my fingers around the current, and the magnetic field is going to point into the page here in the interior of the solenoid. So that's my B external. And of course, if I want that magnetic field to change with time, I'm going to have to change the current as well. Now, of course, I could have a whole extra offshoot of the problem where I take the magnetic field formula made by a solenoid, and I figure out if I want this to change by a certain rate, then what rate would I have to change the current by. That's a pretty easy calculation, but let me not make it part of this problem, because really, I guess I can just tell you right now, all you'd have to do is, this is the rate of change of the current you'd have to make, times these two would give you this rate of change of the magnetic field. But let's just say I cut to the chase, and really the sole purpose of this solenoid is to provide me with a changing magnetic field with time. Now that I have it in this region, at least inside the solenoid, of course outside there is no magnetic field at all, but inside the solenoid I have this rate of change. Now I'm going to put something in this region to react. That is going to be a conducting ring of radius 1 meter and resistance of 2 ohms. So there's my lowercase and uppercase r kind of taken up. So what I'm doing here is I am putting in this region, I guess I didn't specify here in writing what the orientation is, but the writing here, the orientation is going to be something like this. So that right there, there is the radius of my conducting ring. It's 1 meter, so it's inside the solenoid. Its resistance is 2 ohms, and I want to find the EMF generated in that conducting ring. I want to find the current that will be induced, and I want to find the electric field that's underlying and driving that current. And so let's go ahead and we'll do that, and then we'll repeat it if the conducting ring is large, so it's 8 meters, so that would put it outside of the solenoid entirely. So first things first, let's go ahead and put down Faraday's law in its full glory here. So there it is. And let me start by working on the flux part. So the flux, well, that's going to be N B dot dA, although in this case, I really only, my conducting ring itself, there's not multiple turns, there's just one turn, so that's just 1, and then this is BA cosine of the angle between B and A, and hopefully you can see that if I chose the normal here for the computation, it would point into the page, same direction as the field, so this would be 0, cosine of 0 is 1, so this conducting ring is oriented to maximally catch flux from this solenoid. So I basically get back down to the basics. The magnetic flux is B times A. So I'll go ahead and put that in here, and then in this case, both of these are not changing with time. The area is not changing with time, so I'll factor that out. Looks like this, and you can see that the reason I'm going to get an EMF because of a flux change is because the field strength itself is changing, and so I can compute this amount pretty easy. First of all, the area, I have to be careful here. The area, well, this is of course catching flux across its entire cross-sectional area. it doesn't catch everything, but it catches what is actually, it can only catch up to its own size. So A here would be pi r squared. Make sure you understand why it's not pi a squared. It's just not that big. It can't catch all of what the solenoid is throwing. I'm also going to ignore this minus sign here because I'll work out the direction by myself later with Lenz's law. So here I got A times dB dt, and I can put in pi r squared, and then dB dt, just kind of think of it as its own variable. So right there you could certainly plug in, and if you wanted to get that numerically, that is going to be 15.7 volts. So that is the EMF generated in this particular situation. So this conducting ring, there will be a current in it, and that current will be exactly the same as if we connected this thing up to a 15.7 volt battery. Of course, there is no battery in sight. The functional battery is the fact that the magnetic field in the region of the ring is being changed, and that's from the solenoid. So we can go ahead and calculate the current just using Ohm's law. And the current, of course, we take that value divided by the resistance. So 15.7 divided by 2, that should be 7.85 amps. So quite a bit of hefty current. That's pretty large amount of current, but that's just how this example worked out. And so there we have it. And now let's use Lenz's law to work out the direction. So the direction, of course, if this external magnetic field from the solenoid is increasing, remember we said that, if this is increasing, then Lenz's law tells us that B induced wants to fight that change, so B induced is going to want to be opposite that, so B induced is going to point like this. And of course, if B induced points like that, then the current goes the other way. So I induced is going to be counterclockwise. Okay, so this, using Lenz's law, is counterclockwise. So again, I didn't need to do the fancy pants mathematical version of this. I was really looking for this equation just produce a number for the EMF, and then I'll work out separately which way is the current. So that right there, that is the calculation for the current. So we've got the EMF, we've got the current, and now let's look at the underlying electric field. So we can think of this current as being caused in the energy picture by the EMF, or in the forces and fields picture by this weird non-conservative electric field. So let's, whoops, I didn't complete that yet. Let's work that out. My diagram's getting a little messy, so let me just go ahead and just draw the loop back in here. So there's my induced current. There's my induced magnetic field. Oh, and side note, if anyone asks you for what's the net field at the center of the conducting ring, of course, you have B external, which points into the page, and you'd subtract from it B induced because it points out of the page. They're opposite to each other. So if at any given moment you were asked for that, of course, you know the formulas for both of these. This is a solenoid, so you'd use mu naught Ni. If you knew the current at that moment, you'd put it in there. And of course, this is a single ring, so we showed from the Biot-Savart law that is mu naught I over 2r, where this is, remember, this is the radius of the loop. So in this particular problem, we're using little r for that because we've used uppercase R for radius. So if anyone asks you for the B net in the middle, that's what you use. Anyways, it's getting a little off topic. I didn't ask for that in this problem. Focusing in here, the electric field that's driving this points the same way, right? Because positive charges that make up the current also like to follow the electric field. And so going over here to the law, over here, I just use E times L for this. The electric field is constant throughout the perimeter, and 2 pi r. So we have E times 2 pi r is the EMF. So it's pretty much as simple as that. Just take your EMF and divide by 2 pi r. Okay, so that is I'm basically doing a closed loop and following the electric field around as it drives this current around. I do want to also show you, if I plug in my expression from the previous page, my EMF being pi r squared dB dt, this is the same little r, so you will find, and I don't want to spoil away all the surprises, but you will find that the electric field in this region inside the solenoid is proportional to r. So it grows linearly with distance. So as this conducting ring, if it was a little larger, it would have a larger field driving current. So that right there, that is my end of my part A. Again, I have reserved calculating this value exactly, but you can just plug in here and do that. I don't want to spoil all your homework. So let's move on to part B. So part B looks a little funny because now our conducting ring is outside. So it's out here. It's outside the solenoid. And you might be right to question that anything happened there, because of course we said that the magnetic field made by the solenoid, of course, out here is basically zero. If it's an infinite solenoid, its magnetic field is contained entirely inside the core. So you might say, well, nothing happens here. However, I should point out, and another way to argue this is that you have this ring and it is catching some flux, not across the the whole area, but across this inner part, it is catching flux. So, and that flux is changing because the magnetic field strength in that interior region is changing. So by that argument, if we do get a flux change across this ring, we should still get an EMF, still get a current, everything. And in fact, that is the correct argument. Just because the magnetic field is zero out here does not mean that the induced electric field isn't going to be out there still. So we will still have an electric field out here that isn't zero. So that's one thing that I didn't sort of mention earlier when I was talking about this equation, is that this electric field that is induced here does not necessarily have to be in the region of the magnetic field that made it. Okay, so even though there is no magnetic field out here, the induced electric field does extend outside the region of the solenoid. So let's work out the calculation. Pretty much the same thing. So first we'll work out the EMF. And as far as the flux is concerned, now the only real difference is the fact that it doesn't really matter how big this ring is, because the flux, it ceases to be caught, of course, when the magnetic field runs out. So here, we change this part. So we learned that basically this flux was B times A. But now that magnetic field is only caught up to A. So we're basically switching so that rather than the conducting loop size itself limiting how much flux we can catch, now we are capped out at catching the maximum field that the magnetic field, that the solenoid can offer, which is just up to A. So even though now the conducting ring goes out to R, we stop catching flux once we hit A. So now we switch, instead of using pi r squared, we use pi a squared. Now if you're having flashbacks to Gauss's law and just remembering that you have to decide here which variable to put in, it's exactly the same thing. If you're inside, you use r, little r, because inside the solenoid you're limited by your conducting ring's ability to catch stuff. But when you're outside, now this used to be big R in the Gauss's law, but of course we're using that for resistance now, so here outside we use A. So we're essentially limited in the flux we can catch by the size of the solenoid itself. So notice that we now switched. So before we had to use little r, not A, now it's the opposite. So let's work out how this goes. So now I'm just following exactly along with our previous steps. I put it in here. I'll ignore the negative, and I get A dB dt. So again, because the magnetic field is changing with time, and we know that rate, then that's what the EMF comes from. The only difference now is we change over here to the A instead of little r. And so we have this EMF. We can calculate this putting in these variables. We are going to get that the EMF in this case is 62.8 volts. And notice that this does not depend in whatsoever to the size of this ring yet. Okay, so we haven't even used the fact that this particular ring now is, where did I put it? It's 8 meters. So this ring is now 8 meters, but we haven't even used that yet, because at this point we're limited in the flux we can catch simply from the dimensions of the solenoid itself. So we go ahead and we now calculate the current off of it. We're going to assume that this ring changes radius, but it is still 2 ohms. So we'll divide by 2, we'll get 31.4 amps. That's the induced current. And of course, which way is it? Well, the same logic still applies. The magnetic flux from the orange field here, the solenoid, is inward and increasing, so we want to fight that. So I induced is going to go like this and try to fight it. So we do have that the induced current still forms. And then, of course, in the field picture, this is being driven by E induced, which points the same way. So positive charges follow electric field lines. So again, it's strange. Even though the magnetic field of the solenoid is 0 out here, it does still induce an electric field out there when the field in the interior here is changing. Okay, so let's work it out. Same thing. Really, all you have to do is this. If you have this EMF numerically, just divide by 2 pi r. This is where, of course, you would use the 8 meters, get that numerically. Or, of course, let me not spoil all the fun here, but I'll put this in here, and this, pi a squared dB dt, and you divide this by 2 pi r, you're going to get something that's proportional to 1 over r. So now the electric field on the interior and the exterior does die with, oh sorry, there's an equals, that's not an equal sign. So I divide it over here to get the electric field, and it is proportional to 1 over r. So if you look here, if you're getting flashbacks of Gauss's law, it's pretty much the same deal. This here is always the little r. So whether you put the conducting ring inside or outside, that's the radius of the thing that you're inducing current in. And then over here, the only thing that's changed is that this is either little r or a in this case. So there you have it. So if you were to plot, what does this induced electric field look like in the region here? Let's go ahead and sketch that. The electric field that is induced as a function of radius, well, of course, the big separators, whether we're inside or outside the solenoid, so let's mark that off. Inside, it's proportional to r, as we found up here. And outside, it drops as 1 over r. And you can show, of course, although I haven't done it, you can show that they do agree right at the edge of the solenoid. Now, if you're having flashbacks here and saying, wait a minute, isn't this like a infinitely cylinder with uniform rho? So Gauss's law, yes, it's exactly like that. So in the interior, it grew as r and then dropped off. It basically collapsed onto a line charge outside. So basically, it's exactly the same as an infinite cylinder of uniform rho. Now, that's not an accident. The solenoid, of course, here, in some sense, is the magnetic version of a cylinder, right? So instead of a solid cylinder of charge, now this is just a cylinder of current wrapped around it. And so it's no wonder when we extended one dimension to infinity, we made an infinitely long solenoid, that we sort of got the same type of behavior. So the electric field grew as proportional to R inside and then dropped off as 1 over R outside. So it's very, very similar. Hopefully this kind of leads you to see that there are some of these hidden commonalities here between these different kind of classes of problems. This proceeds very much like Gauss's law. Over here it's always little r, and then over here you have to decide if your flux catching is limited by the object itself that you're working with, or in the case of being out here, of course, it's limited by the size of the solenoid, which is sending that flux change. So there you have it. There's that example of which you have a very similar one on the homework, so I didn't want to spoil all your fun.